discussion is via and feedback. We have 5 presentations, 3 big talks and 2 notes. So our first presentation is Annexing Reality, enabling opportunistic use of everyday objects as tangible proxies in augmented reality. Authors are Anuruddha and Wigdor, and Daniel will give a talk.
Thank you very much for the introduction. So I want to talk to you today about this concept of annexing reality. Now, it should be said, of course, that my student, Anuruddha, should be giving this talk. This is his master's thesis work. He slaved away, I assume, 7 days a week, 24 hours a day in the lab while I was off at the beach and whatnot. And of course, this is all of his hard work being represented here, but due to immigration problems, he wasn't able to come to the conference. So let's talk about the state of the art in virtual and augmented reality. We've all been excited by some of the concept videos that have come to us from places like Magic Leap. And the concept, of course, of augmented reality is you wear a see-through display or some other technology that allows you to put digital content over top of the physical world. One of the problems with the state of the art, and even really the fundamental concept of the technologies that are being used today, is that they overpromise and underdeliver on the reality portion of the program. And in particular, if you think about the experience that this video is promising, this user sees a photorealistic, albeit tiny elephant dancing around on the palm of their hand. But of course, they don't feel a small elephant dancing around on the palm of their hand. Now, I suspect that all of you have had this experience. You go to a 3D movie, you put on your Real D glasses, and an object comes right at you out of the screen and comes right up to your face, so close that you can touch it. What do you do in that moment? You reach out and try to touch the object, and what do you feel? You feel nothing but air. So what one thread of research in my group has been trying to do is to address this problem and let you physically feel the virtual content in virtual and augmented reality. Now, there are many technological solutions that exist, and of course Anu's literature review is extensive and all of the papers are cited in our actual paper. But let's talk at a high level. If you really want to feel the real objects, what are your options if you are, say, a developer of a software program? Well, one, you could go back to the physical distribution model of software, which has been abandoned over the last 10 to 12 years or so, and say, all right, if you want to buy our experience, if you want to buy our 3D movie, buy our virtual reality game, you can't just download it from the App Store. Instead, you have to buy it from Amazon, and we'll ship to you these little plastic figures. And then when you're interacting with the content, you can pick up and touch the plastic figure. Now, of course, try telling these software companies that are now used to their 90% profit margins, thanks to digital distribution, that they have to go back to this model, and they'd say, you're crazy. What are alternatives? Well, we could manufacture the objects in the user's home. So you could download the 3D model, and of course we all have maker bots on our desks at home, and we could print out the physical objects, and then we could feel them and interact with them. But that too has, let's call it, refresh rate and latency issues with the experience. Now, there have been other technological solutions to try to address this, of course. One of the most successful, both commercially and in research, is the Phantom device. And I assume that many of you have interacted with this device, but the basic concept is you hold a plastic stylus in your hand, and your motion with the stylus gets constrained in multiple degrees of freedom to create a feeling that you're poking at physical objects. Now, of course, this has the limitation that you have to poke at everything with a plastic stylus in your hand, like someone who's really rude at a Chinese restaurant, right? An alternative approach is something that some of my group did. This is a project that was presented at TEI. Bruno, who's sitting right there, was the first author and presented this earlier this year. And the idea was, when you show a virtual piece of content, add a robotic arm to the space. And so when the user reaches out to touch the virtual content, you take the robotic arm and you set the collision point so that it simulates the physicality of the object. And also the head of the robotic arm turns so that you get the right texture. This falls into the category of what we might call passive haptics. That is, haptic experiences that don't have a requirement of active feedback, like many of the things that we've come to expect, like rumble packs and jets of air and these sorts of things. But of course, this too is, shall I say, a future-reaching version of physical simulation and augmented reality. The robotic arm is not yet ready for production in the home. I say that having seen my students break it the night before the TEI submission deadline. So let's talk about annexing reality. The observation that the project team made was the spaces that people are going to be using their virtual and augmented reality equipment in have physical objects in them already. I don't know where Anu got this picture. Maybe it's an artist rendering of his dorm room. But look at the space, right? You've got nice sharp things, you've got nice soft things, you've got all different shapes. So the concept of annexing reality is when you put on your virtual reality or augmented reality headset, it scans the environment and looks for physical things that are the right size and shape for the virtual content, and then it moves the virtual content and resizes the virtual content to fit on to the existing physical objects in the space. Okay, so we're annexing the physicality of those physical objects for our experience. So here is our system working. Here a champagne bottle is being rendered on top of a Bordeaux bottle. This is not, I mean, of course we all have Bordeaux bottles sitting out, but maybe we don't have the occasion for champagne, and so here we can reshape it. But of course you can imagine all sorts of more dramatic reshapings. So the focus of the project is on how do we enable developers, people who are creating these experiences, to specify the sorts of objects that they want to enable the matching for, and how do we ensure that the tools that we make available to them are done in a way that will allow for good matches. So I'm going to talk about three components here. I'm going to talk about generating what we call the haptic model. We're going to talk about object detection and matching, a quick overview of the algorithm. All the details are in the paper. And then finally, we'll talk briefly about the tracking. So picture yourself as a developer. You are creating a game, and in that game, the character, the user, is going to be interacting with this flashlight. Okay? Now, one option would be you as the developer just create the 3D model of the flashlight, and then the system uses that 3D model and says, all right, I'm going to look for anything that's the same shape and size as a flashlight. I'm going to match that. Now, that, of course, would be over-constraining this search. We wanted a mechanism that would allow us to use all of the knowledge that you have as a designer, where you say, well, I know that the user, because this is a flashlight and you hold a flashlight around the cylinder, the cylindrical base, and point it outwards, that's the part of the physical model that matters most to me. So look for a cylinder. And you know also that because this is an object that the user is going to grasp in their hand, that you can't match any cylinder. It has to be a cylinder that's of a sufficiently small size that the user can actually hold it in their hand. So we take all of the knowledge that you have about the experience you want to have for your user, and we give you the tool to embed that. And that's what we call this haptic model. It's similar in concept to a collision model, but of course different in the ways that I've been describing. So let's talk about the haptic models just a little bit. So on the left here, on the right here, you can see the flashlight. And to its left, you can see our haptic model. It's a wireframe. It'll be hard to see at the back. But we've matched a cone and a cylinder and said that this is the haptic experience that we want the user to have. Okay? Now, there are various properties that you need to set or you can set in order to enable good matching experiences in your game. And I'll take you through what those are. So if you look, for example, at this problem of what if you have an object in the scene, so on the very right, you see a cylindrical salt container that might be sitting on your table. What do you do if there are cylinders in the scene and there's more than one of them? So your champagne bottle is looking for a cylinder and the flashlight is looking for a cylinder. Which one of those do you match? Well, of course, the developer should be the one to decide. It's more important in this experience that the user is going to have a flashlight that they can pick up, and the champagne bottle can just be decoration. So you can set a preference to say that it's more important to match the flashlight. What about the inverse case? In the inverse case, we have one model and more than one object that might match the different primitive shapes. So here on the right in the circles, you see we have the same salt container, and we have also a cone, a party hat, in the scene. And either of those might match the two primitives of the haptic model, the cylinder of the handle and the cone of the lamp of the flashlight. And here too, the developer, as I alluded to before, says it's more important that they have a cylinder to grasp, and so I'm going to match that. So I prioritize that primitive in the model. And then, of course, we also allow the developer to specify which properties are the most important. So if there are two physical props here that are both cylindrical, like the salt container and the garbage can, well, we say the salt container is a better match because it can be grasped in the hand. And we enable the developer to do that by specifying that the radius has the highest priority when doing the physical matching. Now, of course, I realize that this dialog box, the actual text, is way too small for you to see, and all the details are in the paper and the video. But that's the high-level concept. So here is the environment. Here is his actual prototype. He's got augmented reality glasses and a Kinect sensor on top, and it scans the environment. And just at a high level, he detects the dominant plane that the objects are sitting on. He then does 3D point extraction, foreground and background subtraction to find objects. Then does clustering to detect what are separate objects. And then finally does primitive shape matching, and only primitive shape matching. Now, the contribution of this work is not in the computer vision algorithms. These were all taken from existing work in computer vision, and of course, it's all cited in the paper. But once we have all of these primitive shapes, then we can do our matching algorithm. It's essentially a constraint solver. And in the middle, we have the virtual objects. We have a champagne glass, a donut, and a flashlight. And it goes through and evaluates all of the constraints that the developer has set and finds the optimal match based on all the properties. And finally renders or yields to us that there will be a final matching where the champagne bottle will get matched to the Bordeaux bottle, the donut to the neck pillow, and the flashlight to the salt container. And then, as you might expect, we don't do this matching for every frame. We do the matching once when a new object is entered into the scene or when the scene starts up to do the initial alignment, and then finally do iterative closest point tracking to make sure that the system is performant. So here is the result of the example that I just gave. So this developer said, yes, this donut can be comically large, and we want it to be able to match. Maybe this is the Homer Simpson experience that the developer wants the user to have. And we see the flashlight has been matched and the wine bottle has been matched. Now, given these developer experiences that we wanted the user to have, our developer users to have, we wanted to understand, could developers understand all of the constraints and build these haptic models in a way that were useful? So we ran a study. We brought in professional developers and professional 3D modelers from the Toronto area, and we asked them to build haptic models and then evaluate whether or not they could anticipate the matching. We measured first the utility, and we asked the question, are the developers able to express their design intent as a haptic model, a set of primitive shapes, priorities, and scaling parameters? And then if the system is useful, if it has utility, we were also, of course, concerned with usability, and are they able to use the system that we built to do their matching? So we had 8 professional developers, each time trying to match a set of objects. We had 4 trials for each object and 32 in total for each developer. And it went like this. So picture yourself as a developer. You come into a room. We would show you a virtual model. So you'd see the champagne bottle, the virtual champagne bottle. We would say, imagine the sorts of physical objects that might be in a space that you might want to match that to. And now create a haptic model. And of course, we gave them instructions to understand how to do that. We then brought out a box of props and said, okay, now that you've created your haptic model, take these props and categorize them into those objects that will match your model and those objects that won't. And of course, the goal here is to understand, could they understand the implications of their model? And then finally, for the set of objects that will match, which one would get matched first if they were in the same scene together, the same living room together? And then finally, we observed the results. Now, we're very pleased to say that in all 32 trials for 8 developers, the developers were able to perfectly separate the props into will match and won't match, and so they were able to express it in that way. In only 19 of the 32 trials, though, were they able to say which of the will match group would get chosen first if they were all in the same scene. So that suggests more experience is necessary, perhaps a better mechanism to enable them to specify their intent. On the usability, excuse me, still on the utility, but on a rating scale, we asked them, given the sorts of game experiences that you are creating and you might want to have physical experiences for, are primitives enough? And we got the response, a mean of 4.5 out of 5 saying yes. Is the priority scheme useful? 4 out of 5. And is it easy for you to predict? We had our study results, and they themselves said only 3 out of 5 times could they predict. So we have that usability issue potentially. We asked them to rate their ability to learn the constraints, 5 out of 5 on ease of use, worked without leading to errors, 4 out of 5, pleased with the performance, 4 out of 5. All the details are in the paper. So just wrapping up, there are a couple of examples that we found really interesting when we were working with the developers. One was the Lightsaber. So picture yourself making a Jedi game where you want the user to be able to have a lightsaber experience. Now, would you create a haptic model that just matches the handle of the lightsaber, so just the part the user holds, or would you make it match the entire lightsaber, including the, what do you call the sticky part of a lightsaber? The light? Anyway, the whole thing, okay? And it turns out that there are very different implications depending on the experience that you want the users to have. If you want users to be able to hit each other on top of the head, then it's important to match that whole thing and only match it to things like broomsticks. If, however, you just want them to be able to hold the lightsaber and swing it around, then you can just match the handle. Okay? One problem we observed that came up in our matching, for this lamp model, users matched the cylinder, the shade of the lamp. But the cylinders we had in the space were sitting on the table. So what this meant was when it matched the shade of the lamp, the actual body of the lamp would be through the table. So there was this sort of physical collisions that weren't anticipated in our system, and that's something to explore further. But I am happy to say, as my laptop goes to sleep, oh no, the display driver failed. That's okay, I was wrapping up. The fundamental concept of augmented reality and our annexing reality on top of it was able to create these sorts of haptic experiences, and we think it's an area ripe for further exploration. So I'll stop there and take your questions.
We have time for a few questions.
Hi, Alexandra Ayan from HPI. I was wondering, did you also take into, so great work by the way, I also love the TI submission, and have you considered taking into account material properties? So it was like very apparent with the pillow and the donut,
yeah.
And it would be great to integrate that.
Yeah, you're absolutely right, Alex, that what we have to think about next is what are the other properties of the object? So Anu picked up a thermal camera, for example, so that it would stop matching this burning hot plate in the space to a record. That didn't work very well. And absolutely, if we can do further recognition or otherwise, either say we know this is a pillow and here's its material property, or use computer vision techniques to recognize the material properties, then we can bring it in. The interesting thing that happens, of course, is there's this temptation to over-constrain. Mm-hmm. What you want is there to be a lightsaber sitting there that you can pick up, right? So as you bring in more and more of these properties, I think the opportunity for the developer experience is to say, how can you give the developers intuitive tools to create a good experience for the user without just completely overwhelming them with this parameter space. So yeah, it's interesting.
Okay, thanks.
Hi, I'm Misha from the Media Lab at MIT. I was wondering if you were actively doing object recognition, or it was something, in real time, as opposed to something that you had already pre-built and recognized, and then you were using the objects in the space.
So if we're going to get precise about the vision language, I'll say we're not doing object recognition in the sense that we say we know that's a pillow. We're saying we recognize the shape of this thing is a donut. But yes, it is real time. And all of the algorithms are referenced in the paper. We didn't iterate, other than trying to apply them to our specific constraints. The contribution here isn't in the vision, and we don't, I don't want to overclaim, right? But
I was just curious.
Yeah, absolutely. It's done in real time. The latency is kind of lame when you start moving things around, but that's someone else's problem. We'll do the high-minded concepts and move on.
Thank you.
Okay.
Hi, Doug Bowman from Virginia Tech. So this is really nice work, and it works really well for cases where you've got small objects that can be grasped by the hand, and you don't really care where they are in the scene because the user can move them around.
Right.
Have you thought about how to annex large objects that need to be in a specific place in the scene?
Mm-hmm. Yeah, so the original concept actually was about annexing functionality. So it would say, like, if you need a keypad, recognize that there's a keypad over there, and you can use it for button entry, or if you want a touch screen, see that there's a touch screen there. And we ended up starting just with the object stuff. I think my sort of absolutist answer to your question would be, I would rather provide developers with a way to describe their scenes in a way that can be reconstituted to the environment, and think about doing it that way rather than sort of doing it the other way. But you know, clearly there's the scalability issue here that we need to address. Okay.
Thank you, Daniel.